Welcome back to the deep dive. We take the source material, break it down, and pull out the key insights so you get informed fast.
Exactly. No getting bogged down.
So today we're digging into Chapter 3 of Stahl's Essential Psychopharmacology. We've got the groundwork from Chapters 1 and 2.
The foundation.
And now we're looking at, well, how drugs actually interact with ion channels in the brain.
Yeah, this chapter gets right into the mechanics,
Yeah.
how these channels work, how meds can tweak them.
Right. And for you, our listener, the learner, we're aiming to make this super clear, engaging, distill it down.
Get those aha moments going.
Okay, let's jump in. First, big definition from Chapter 3, ligand-gated ion channels. What exactly are we talking about here?
Okay, so ligand-gated ion channels. Think of them as special doorways or receptors on the surface of a neuron in the cell membrane.
Doorways, okay.
And they only open or close when a specific molecule, the ligand, binds to them. A neurotransmitter is a perfect example of a ligand.
Like a key for the door?
Exactly like a key. The ligand is the key. The channel is the lock and gate. When the key fits, the gate swings open, or sometimes shuts.
And what goes through the gate?
Ions.
Yeah.
Charged particles. They flow into or out of the cell, and that movement, well, it rapidly changes the cell's electrical state. It's fundamental.
Got it. So, tiny chemical keys controlling electrical flow. Makes sense. Now, why are these channels such big targets for psychotropic drugs? Why focus on them?
Well, because they're right at the heart of brain communication. I mean, fundamentally.
Okay.
That flow of ions across the neuron's membrane. That is the nerve impulse. It's how neurons talk to each other, how signals get sent.
Right, the actual message.
Precisely. So if you target these channels with drugs, you can directly influence things like, well, how easily a neuron fires, how many neurotransmitters get released. Basically, you're tweaking brain function at a very basic level.
Which ultimately affects mood, thought, behavior.
Exactly. So for you listening, understanding these channels, it's really step one in figuring out how these medications actually work deep down.
Okay, crucial stuff. Now, Chapter 3 really unpacks ligand-gated channels, and one thing that jumped out is this idea of the agonist spectrum.
Ah, yes, the spectrum.
Can you walk us through that? It mentions full agonists, partial agonists, antagonists, even inverse agonists. Sounds like a range.
It absolutely is a range. The agonist spectrum just describes all the different kinds of effects a ligand can have when it bumps into that receptor.
Okay.
So at one end, you've got your full agonist, this molecule binds, and bang, you get the maximum possible response from that receptor.
Huh.
Think of it like flipping a light switch all the way on. Max brightness.
Full power. Got it. What about partial agonists then? Sounds like less power.
Kind of, yeah.
Yeah.
A partial agonist also binds and activates the receptor, but it only produces let's say, a submaximal response.
Okay.
Even if every single receptor is occupied by that partial agonist, you don't get the full effect. The light switch only goes halfway up, maybe medium brightness.
Right. So it activates, but not fully.
Exactly. And here's where it gets interesting. Partial agonists can act differently depending on what else is going on.
How so?
Well, if the body's natural full agonist, the main neurotransmitter, isn't around much, the partial agonist can step in and provide some activation. It acts like a net agonist, boosting the signal, increasing ion flow a bit.
So it helps out when the main signal is weak.
Precisely. But, and this is the cool part, if there's too much of the natural full agonist floating around,
Yeah.
the partial agonist competes for those receptors. And because it produces a weaker signal, it actually brings the overall response down. It acts like a net antagonist in that situation.
Whoa, okay, so it can boost a weak signal, but dampen an overly strong one.
You got it. It's like it stabilizes the system. It prevents the highs from being too high and the lows from being too low. That's why they're sometimes called stabilizers. It's a much more nuanced approach than just full on or full off.
That's fascinating. A real fine-tuning mechanism. Okay, so that's partial agonists. What about plain old antagonists? They just block things, right?
Pretty much, yeah. An antagonist binds to the receptor, often quite strongly, but doesn't activate it at all. It just sits there.
Occupying the space.
Exactly.
Yeah.
It blocks the natural agonist or any other agonist from binding and doing its job, like putting tape over the light switch so no one can turn it on.
Simple blocker. Makes sense. And the last one, inverse agonist. That sounds counterintuitive. Opposite of an agonist.
It is a bit weird sounding, but yeah, it does the opposite.
Yeah.
Many of these channels have a certain level of activity, even when no agonist is bound a kind of baseline hum.
Okay, a resting state that isn't totally off.
Right. An inverse agonist binds and actually reduces that baseline activity. It makes the channel quieter than its resting state. actively turns the light dimmer than it normally is when off.
Wow, so it actively suppresses the channel's function below baseline.
Precisely. It's not just blocking activation, it's actively promoting an inactive state.
That's a powerful effect. I can see how that might be useful. Maybe we'll see examples later.
Definitely something that comes up when discussing specific drug actions down the line.
Okay, so that covers the spectrum of direct interactions. But Chapter 3 also brings up allosteric modulation. What's that about? Sounds different.
It is different. Allosteric modulation is more like influencing the receptor indirectly.
Okay.
These modulator molecules, they don't bind to the main spot where the neurotransmitter binds the primary or orthosteric site. They bind somewhere else on the receptor protein.
A different location on the same receptor.
Exactly. And binding there doesn't directly open or close the channel. Instead, it changes the receptor's shape slightly, which in turn affects how well the main ligand binds or how effectively it opens the channel when it does bind.
Ah, so it's like adjusting the sensitivity of the main switch rather than flipping it directly.
That's a great analogy. Perfect. And you have two main types.
Okay.
Positive allosteric modulators, or PAMs. They bind and make the receptor more sensitive or responsive to the main agonist. The neurotransmitter becomes more potent.
Like turning up the volume knob for the main signal.
Spot on. Same amount of neurotransmitter gives a bigger effect.
Yeah.
The dimmer switch goes brighter more easily.
Got it. And the other type must be
Negative allosteric modulators, NMs. They do the opposite. They bind to their allosteric site and make the receptor less responsive to the main agonist.
turning the volume down.
Exactly. They diminish the effect. So PAMs and NMs offer this amazing way to fine-tune channel activity without directly blocking or activating the main site. It adds another layer of control.
And the chapter mentions these channels aren't just open or closed, right? There are other states.
Oh, yeah. It gets even more complex.
Yeah.
They can be resting, open, closed, but capable of opening inactivated, meaning temporarily shut and unable to open, and even desensitized, where they stop responding even if the ligand is still there. Lots of states.
Wow. So much complexity in these tiny things. Okay, shifting gears slightly. Chapter 3 also covers voltage-sensitive ion channels. How are they different?
The key difference is the trigger. Ligand-gated channels need that chemical key, the ligand. Voltage-sensitive ion channels, as the name suggests, respond to changes in the electrical voltage across the cell membrane.
So not a chemical signal, but an electrical one opens the gate.
Precisely. Think of them as having built-in electrical sensors. When the charge difference across the membrane changes sufficiently, these channels sense it, and that causes them to open or close.
Like a motion sensor light, but for electricity?
Sort of, yeah. It detects a change in the electrical field.
How do they actually do that sensing? What's the mechanism?
Well, the structure is pretty neat. They're made of proteins that snake back and forth across the membrane. Stahl mentions typically 6 transmembrane segments per subunit in the pore-forming protein.
Okay.
And one specific segment, often segment 4, is loaded with charged amino acids. This part acts like a tiny voltmeter.
A voltmeter built into the protein.
Yeah. It physically moves in response to changes in the membrane voltage. And that movement pulls on other parts of the protein, ultimately opening or closing the central pore that lets ions through.
That's incredible. Ingenious design.
It really is. And this general structure, this idea of transmembrane segments with a voltage sensor, it's a common theme. You see it in both voltage-sensitive sodium channels, VSSCs, and voltage-sensitive calcium channels, VSCCs, although the specific proteins are different, of course.
Allowing them to be selective for sodium or calcium ion?
Exactly. Different channels, different ions, but a similar voltage sensing mechanism.
Okay, so we've got ligand-gated, responding to chemicals, and voltage-sensitive, responding to electricity, both absolutely critical. How does understanding all this detail, the spectrum, the modulation, the voltage sensing, help us with the bigger picture of treating mental health conditions?
Well, it's the foundation for almost everything that comes next in psychopharmacology. These principles we just talked about, they'll pop up again and again when we look at specific drugs.
Okay.
Like think about epilepsy treatments. Many anti-seizure meds work by targeting those voltage-sensitive sodium or calcium channels, trying to calm down excessive neuronal firing.
Ah, directly applying that voltage-sensitive channel knowledge.
Exactly. Or think about anxiety. Some anti-anxiety drugs, like benzodiazepines, are actually PAMs. They bind to the GABA-A receptor, which is a ligand-gated chloride channel at an allosteric site.
So they're not mimicking GABA directly.
Nope. They make GABA better at opening the channel when it does bind. that enhances inhibition in the brain.
I see. So understanding PAMs is key there.
Totally. So for you listening, grasping these concepts, agonists, antagonists, partials, PAMs, NAMs, ligand-gated versus voltage-gated, it's essential. It unlocks how drugs for psychosis, depression, anxiety, mood stabilization, how they all actually work at the molecular level.
It really does feel like Chapter 3 gives us the toolkit, the vocabulary we need for what's coming next. Okay, let's try and summarize the big takeaways from this dive into ion channels.
Sure. I'd say the main points are, 1, ion channels, both ligand-gated and voltage-sensitive, are absolutely fundamental for neurons to communicate. They control the electrical signals.
Right, critical infrastructure.
2, drugs can target these channels in really diverse ways. They can mimic the natural ligand, block it, partially activate the channel, or subtly tune its sensitivity using those allosteric sites.
The whole spectrum and modulation piece.
Exactly. And 3, understanding these different mechanisms is just, well, it's crucial if you want to understand how any psychotropic medication actually produces its effects in the brain. It's the basic science behind the treatment.
Absolutely. And I have a feeling these ideas, ligand-gated, voltage-sensitive, the agonist spectrum, PAMs, NEMs, we're going to hear those terms a lot as we continue through Stahl.
Oh, definitely. They're recurring themes, for sure.
Okay, so here's a final thought to leave you with. Just think about how these incredibly tiny, intricate mechanisms, these channels opening and closing in fractions of a second, responding to chemicals and voltage, how all that translates into the richness of our thoughts, our feelings, our behaviors every day.
It's mind-boggling when you scale it up.
It really is. And what could really understanding these channels even better unlock for future mental health treatments? Something to ponder. Thanks for joining us for this deep dive.